Okay, I think we are more or less approaching the great moment. So my name is Harald Brune, and I would like to welcome you in the name of the Institute of Physics and also in the name of the students, of course. And it's my pleasure to introduce our next speaker. And the next speaker is known to many of you simply from the fact that he has written books in quantum mechanics, I think, which are really read by many of us. And I myself, as a student, I was reading these 2 volumes of quantum mechanics, and I heard that there's a third one now that appeared. So this is from my experience with Cohen-Tannoudji. So far, I did not listen to your presentations, and I'm really looking forward to this. So Cohen-Tannoudji did his PhD in '62 at the École Normale Supérieure, and then he moved to the University of Paris, where he became a promoted full professor in '67, and he taught lectures on quantum mechanics, and this is really the moment when you started to write these books together with colleagues. And in '73, he was moving to the Collège de France. He became a professor in Collège de France, and at this moment, he created basically a laboratory who's world famous. And this laboratory has studied techniques, how you can trap atoms and how you can cool atoms. And the laboratory was created together with Alain Aspect, Christophe Salomon, and with Jean Dalibard. And the work that has came out of this laboratory actually has been rewarded the Nobel Prize in Physics in 1997. For having introduced methods that are suited for cooling atoms and for trapping atoms. So we are now very much looking forward to your presentation, and I give you the floor.
Thank you very much for your presentation, and let me also thank Clément and Jacques for inviting me to this Physics Day with the students. I like very much to talk in front of students and try to motivate them for doing science. So I was initially planning to speak in French, but Clément told me that it would be better to translate my talk in English, so I will do it in English. So the title is Manipulating Atoms with Light. You know, the elementary interaction processes between atoms and photons, which are the basis of what I will describe today, consist of emission process, where the atom starts from an upper state to a lower state by emitting a photon with frequency nu and energy h nu, where h is the Planck constant. And you have also the absorption process, the reverse process, where the atom starts from A and goes to B by absorbing a photon. Of course, you have this equation, which expresses the conservation of energy. The photon which is emitted or absorbed has an energy which corresponds to the difference of energy between the 2 states between which absorption or emission takes place. So if by a spectrometer you measure nu, you get the energy difference EB minus EA. That shows you that light can be first considered as a source of information on atoms. And that's the principle of spectroscopy. By measuring the spectrum which is emitted by an atomic system, you can determine its energy levels. And spectroscopy in all frequency ranges, starting from RF and going to gamma ray. So light, first, can be considered as a source of information. And that's important because if you take, for example, 3 different atoms, they have not the same lines because the energy levels are different. You know, in fact, a spectrum of light can be considered as some sort of a fingerprint of the atom. So by looking at the light which is emitted by a medium, you can know what are the atoms which are in this medium. And also, you can get information about the universe by looking at the radiation that you receive from the universe. And until last year, the only source of information we had on the universe was coming from the observation of light, electromagnetic radiation in all frequency range. And you know that now we have another source, which is gravitational waves, which is very important because now we have a new window for looking at the universe. But what I would like to show you in this lecture is that is also a tool for acting on atoms, for manipulating them. And that's easy to understand because when an atom absorbs or emits a photon, it gains certain properties of this photon. Its energy, its linear momentum, its angular momentum. And you see that's what is called basic conservation law, conservation of the total energy, of the total momentum, linear and angular. So by choosing the property, by choosing the light which excites an atom, you can change its property. And that's the idea. First example, optical pumping. That was in the 1950 when Alfred Kastler and Jean Brossel, at a time where lasers were not existing yet. They were using just lamp sources, discharge sources. But they have shown that by absorbing polarized light, atoms can have their momentum, angular momentum, change, and they can become oriented, spin-oriented. And you can also, that's important, I will show you, that you can detect the transition, the RF transition between different sublevels by modification of the amount of light which is absorbed or emitted. And that's a big step. And Alfred Kastler got the Nobel Prize in 1966 for this method. And the second example is laser cooling and trapping. Because photons have a momentum. And now with laser beam, you can excite an atom with a lot of photons, having all the same momentum, linear momentum. And by transfer of this linear momentum to the atom, you can push the atom, you can change the velocity, and you can put this velocity to very low value. You can cool them at extremely low temperature, and you can also trap them. And that's the field of laser cooling and trapping ultra-cold atoms. Let me first discuss the transfer of angular momentum and the polarization. Suppose that you have a cell here containing atoms, and suppose that you excite, for example, sodium atoms, and you can excite this cell with a light beam which is circularly right polarized. The electric field of the light rotates like that. And suppose that you are exciting a transition between two levels, G ground state and E excited state, having both an angular momentum 1/2. And you know that angular momentum is quantized in quantum mechanics. That means that the angular momentum can be either plus 1/2 or minus 1/2. You can imagine the atom having a small magnetic moment, either up or down, both in the lower state and the excited state. Now, when you look at the angular momentum of light, you can demonstrate that a right circularly polarized light consists of photons having all an angular momentum plus 1 in units of h bar, h over 2 pi. So when an atom absorbs a sigma plus photon, it gains a momentum plus 1 in units of h bar. And if you look at all possible transitions connecting these two states to these two states, the only transition where the angular momentum increased by 1 unit is from minus 1/2 to plus 1/2. In this case, you have 0, minus 1/2, minus 1/2, 0. And in this case, you go from plus 1/2 to minus 1/2, you have minus 1, sigma minus photon. So if you excite atoms with sigma plus light, the only transition which can be excited is this one, from minus 1/2 to plus 1/2. So atom absorbs a photon, goes to plus 1/2, and then an excited state in atomic physics is unstable. After a certain time, which is the lifetime of the excited state, the atom comes back to the ground state by emitting a photon. And you see, it can emit a photon either that way or that way, because that's spontaneous emission. If it emits a sigma plus photon, it comes back here, and it can repeat the cycle. If it emits a pi photon has a zero angular momentum. It goes to this state, between +1/2 and +1/2. And when it is here, there is no sigma plus transition starting from +1/2 for a transition connecting two levels with angular momentum 1/2. So it is trapped here. So, and then you can accumulate atoms in this state. And if you look at this picture, it's like a pump, which pumps the atom from this state for putting them in this state. This is why it's called optical pumping. It's a pump using absorption of polarized light and emission of polarized light. And that's very interesting, because you can reach degrees of polarization as far as 90%. 90% of the atom can be put in this state. And it's not easy, in general, to polarize atoms. You have to decrease the temperature. And if these two levels are separated by a very small energy, compared to KT, the thermal energy, the difference of population, thermal population difference, is completely negligible. The two states are absolutely equally populated. By optical pumping, you can realize very strong population difference. And so that's a pump. Another important point is that absorption of light can take place only from the -1/2 state. So by looking at the amount of absorption light, you have a signal which is proportional to the population of the -1/2 state. And any change of this population, produced, for example, by magnetic resonance transition between the two spin states in the ground state, can be detected optically by a change of the amount of light which is absorbed. So you have a very sensitive optical detection of magnetic resonance. So you have both advantages. You polarize atoms, and you can detect optically, very sensitive, all population difference of the two, between the two ground state sublevels, population difference which can be changed by RF transition or by collision. So that gave rise to a lot of fundamental and practical application. Let me just give one of them. MRI, imaging of the empty part of the lung. Because you can polarize helium-3 atoms by optical pumping and have a patient breathing a mixture of air and helium-3 polarized by optical pumping, and you can make MRI. Usually, MRI use magnetic resonance on the protons of the water molecules. And the water molecule of the blood, you detect only the solid or liquid part of the body. Helium-3 goes to the empty part of the lung, and you can detect this empty part. And that was very interesting, because you can detect disease like asthma, smoker, and stuff like that. And you have a lot of other applications, which I have no time to describe in detail here. Let me give you another important point, which was discovered during the beginning of optical pumping, and which was actually my thesis work. In fact, if the light is not exactly resonant with the transition between the ground state and the excited state, if it is non-resonant, one can show, theoretically and experimentally, that the ground state is shifted by light. For example, I have represented here the ground state, the excited state. If the light which excites the system has a frequency omega L larger than the atomic frequency, the ground state is shifted by a positive amount, delta Eg, which is called the light shift, and which is proportional to the light intensity. If the light is detuned to the red, smaller than omega A, the light shift is negative. The shift is shifted downward. So you have the possibility, by changing the intensity of the light or the frequency, to control the energy of the lower state, to change it. Of course, you could change it also by applying a magnetic field, a static magnetic field, and using the Zeeman effect. But with a light beam, you can focus the light very, very tightly, and you can produce a light shift on a very small distance. And in general, two ground state sublevels, G1 and G2, have different light shifts, because the polarization of the line starting from these two levels is not the same. So the light can change the splitting between the two sublevels. And if you look at this effect, you can consider it from two different points of view. First, it's a perturbation. It perturbs the energy levels. And if you are interested in measuring very precisely the Zeeman splitting in the ground state, it's a perturbation. You have to correct your measurement to extract the real splitting. You have to make the magnetic resonance at different light intensity and extrapolate to zero intensity. But what is strange is that effect was discovered in 1960. So now, 30 to 40 years after, it turned out that with laser beams, light shift can be interesting. Very interesting, because they can be used to manipulate atoms. And I will show you that in the next transparency. Remember, at that time, we were using only light, ordinary light emitted by thermal sources. For example, I come back to my transition between two sublevels of the ground state and two sublevels of the excited state. So you see that depending, if you excite with sigma plus light, you shift only this state. If you excite with sigma minus light, you shift only this level, because you have only this transition or this transition. So the splitting between the two sublevels is changing. Okay, so the magnetic resonance optically detected with the resonant beam and slightly resonant undergoes a light shift which depend on the polarization of the shifting beam. And that was the first experiment done in 1961, when you see the ground state resonance in the absence of perturbing beam, and the magnetic resonance with a sigma plus beam or sigma minus beam. You see that the magnetic resonance curve is shifted by light and by different amounts, depending on the polarization of light. You know, at that time, the shift was only 1 hertz, because the light beam was very weak. But now with laser beam, you can get light shifts as large as gigahertz, very, very big light shift. And let me just remind you a joke of Alfred Kastler. He was calling this effect lamp shift, because the light shift produced by the interaction of atom with light reminds another important effect, which was discovered by Lamb, and which was due to the interaction of the atom with the vacuum field, the quantum vacuum field, and which is not the same for the 2s and 2p state of the atomic hydrogen. And this slight difference was the starting point of QED, quantum electrodynamics. It was called the lamp shift. And he called it, this effect, he called it lamp shift because it is produced by the light coming from a lamp. Okay, so let me now go to the second example, which is laser cooling and trapping, and which comes from the transfer of linear momentum from photons to atoms. And that's easy to understand, much easier than optical pumping. Because if you look at an experiment, you have a target bombarded by a beam of projectiles coming all from the same direction and bouncing on the target, you know that as a result of the transfer of linear momentum from the projectile to the target is pushed. The same thing occurs if you replace the target by an atom and the projectile by photons, which are absorbed and re-emitted in random direction by the atom. And as a result of this bombardment, as a result of this transfer of linear momentum, the atom is pushed. And that's what is called radiation pressure. And it is well known, because if you look at a comet, the tail of a comet comes from the projectiles which are from the particles around the comet which are pushed by the light coming from the sun. That's exactly an effect of radiation pressure. But if you replace the light coming from the sun by a laser beam and project the small particle by atoms, then the radiation pressure can be much higher. Let me give you an order of magnitude. An atom absorbs a photon and re-emits a photon in all random directions. So the transfer of linear momentum comes only from the absorption. It gains a momentum h nu over c, because the momentum of a photon is h nu over c. Because the momentum which is taken away by the emitted photon is zero on the average. So in each cycle, the mean velocity change of the atom is equal to delta v, the recoil velocity, which is the photon momentum, h nu over c, divided by the mass of the atom. Because you have h nu over c, the momentum of the photon, equals mv, the recoil momentum of the atom. So the recoil velocity is h nu over mc, is here, excuse me, here. And when you take the number, you find that this is on the order of a centimeter per second. So an atom absorbing and emitting a photon, on the average, its velocity changed by 1 centimeter per second. That's very small. But after a cycle absorption-emission, the atom is still on the laser beam, and it can reabsorb the second photon, a third one, a fourth one. How many photons can it absorb? Each cycle, absorption-emission, lasts a time which is tau, the mean lifetime of the excited state. And the radiative lifetime of excited state is typically 10 to the minus 8 seconds. It's a very short time. So in 1 second, you can have 10 to the 8th cycle. And the recoil velocity per second is equal to the velocity change per second times the number of cycles. So that is equal to h nu over mc, v recoil, times 1 over tau, which is 10 minus 2, that's the recoil velocity after 1 cycle, times the number of cycles per second, 10 to the 8th, and you find the recoil, the mean recoil velocity per second, not per cycle, per second, is equal to 10 to the 5. And you 10 to the 5, yeah, and 10 to the 6, excuse me. And you know that the acceleration due to gravity is 10 meters per second squared. So the force exerted by a light beam on an atom can be 10 to the 500,000 times bigger than the force due to gravity. So that's a huge deceleration. And if you have an atomic beam coming in that direction and the laser beam counterpropagating, if the atoms are starting with 1 kilometer per second, with the radiation pressure of the light beam, the laser beam, it can be stopped in V0, 10 to the 6, divided by A, the acceleration, so it gets 10 to the minus 3rd second. In 1 millisecond, the atom can be stopped, starting from 1 kilometer per second to 0, and during this time, a simple calculation shows you that it travels about 1 meter. So an atomic beam with atom of 1 kilometer per second velocity, initial velocity, can be stopped in 1 meter. That's very interesting, because then you stop atom, and you get the following experiment. The atoms come like that, the laser beam comes like that, but there is a problem. When the atoms start to decelerate, of course, their velocity changes, and you have the Doppler effect. So if the laser beam is resonant at the beginning, after a short distance, it will be off resonance because of the Doppler effect, and the force will decrease. So to solve this difficulty, people, in particular Bill Phillips, one of my colleagues, has the very beautiful idea to put the atom inside the solenoid with producing an inhomogeneous magnetic field which varies in space, and calculated in such a way that the change of the frequency due to the Doppler effect is compensated by the change of frequency of the laser beam due to the slowing down of the atom, so that the atom remains in resonance all the time with the laser beam. And that's called a Seemann slower. And for example, you see this picture, that's the exit of the magnetometer, here of the magnetic field. And you see the sodium beam here coming from the magnet solenoid. Stop, you see here the stopped atom. So you can see by eye the laser beam stop, and you get a ball of cold atoms, slow atom at this point. And that's called a Seemann slower, and it's called also a molasses. Another solution also is to take the laser beam, and now it's very easy to change the frequency of the laser beam and to chirp the laser frequency, to remain it, to have it all the time in resonance with the atoms. Now, once you have stopped the atom, you have not cooled them, because the temperature in physics is not related to the mean velocity of an ensemble of atoms. It's related to the velocity spread around the mean value. So if you want to cool atoms, you have also to reduce the velocity spread around the mean value. Of course, it's very nice to have the mean value equal to 0, but then you have to reduce the velocity spread. How can you do it? And the first suggestion was given by Hans Shallow and Demelt, and it was using the Doppler effect, and instead of using a single laser beam, they were proposing to use two laser beams counter-propagating with the same intensity and with the same frequency, slightly detuned below resonance. So you have the atom here, and the two laser beams with new laser smaller than nu A. If the atom is at rest along this direction, you have no Doppler effect. So the two apparent frequencies are the same, and the forces are equal and opposite. The total force is equal to 0. So no force. If the atom is moving to the right here, because of the Doppler effect, the frequency, the apparent frequency of this laser will increase because of the Doppler effect, and it will get closer to resonance. And the apparent frequency of this laser beam will decrease because of the Doppler effect, and we get farther from resonance. So because of the Doppler effect, the two frequencies change. One increases, the other one decreases. They are no longer the same, and as a consequence, the total force will not be the total force will no longer be equal to 0. You will have a force equal to the lower frequency beam. You will have a force equal to the difference of two forces, and for small linear velocity, it will be linear in V. So you will have a force, a slowing force, linear in V. And a force linear in V is nothing but a friction. The faster the system moves, the stronger the slowing down force is increased. So you have a slowing force which reduces now the velocity spread, and you cool the atom. And this is called Doppler cooling, because it's a cooling due a mismatch between two forces due to the Doppler effect. And you can calculate the velocity spread you can get with this force, and you get velocity spread corresponding to temperatures of the order of 1 millikelvin, which is already very nice. But the big surprise is that when people started to measure this temperature, they found a complete difference with theoretical prediction. Let me first tell you how they measure the velocity spread. Once the cloud has been cooled, what they do, they switch off the laser beam. So the atom falls, and the cloud increases because of velocity spread, and by using the second laser beam downward, they can measure the velocity spread of the atom. It's the time of flight. And they measure the velocity spread and consequently the temperature. And the temperature was not, the measured temperature was not 1 millikelvin, but on the order of 1 microkelvin. So something else happens. And this is where light shift appeared to play a role. That was not expected at all. And this is a cooling scheme that we call with my colleague Jean Dalibard, Sisyphus cooling for the following reasons. So suppose you have two ground state sublevels, spin up and spin down, like as I explained just before. If you have two laser beams counterpropagating, having a different polarization, you have a standing wave. So the intensity of the light oscillates in space. So the light shift, if the light is detuned, the light is detuned in laser cooling. The velocity, the energy of the Zeeman sublevel will be modulated in space. And in general, the two sublevels will have different modulation. But you are not detuned too far. So you still have absorption of photon and remission, and you still have optical pumping from one sublevel to the other one. So you have both light shift and optical pumping taking place. And what happens is the following thing. For example, the spin down state has the energy levels as a function of position, which is oscillating like that. The other state has an energy which is also modulated in space, different from the previous one. And you have optical pumping from one state to the other. And the correlation can be such that when the atoms in these sublevels climb this potential hill, it is optically pumped to the other state, which is the bottom of a valley. And it has to climb again and things like that. So exactly the situation of the hero of the Greek mythology, Sisyphus, who was condemned to put a rock at the top of a mountain, and then the god was putting it downstairs, and he had to do the job again and again. And at each of these cycles, the energy of the atom is decreasing by this amount, and after a certain number of cycles, it's a very low temperature. And when you do the calculation of this scheme, you find a result in good agreement with the experimental observation. And that reached 1 microkelvin, 10 to the minus 6 Kelvin. Now, can you go further? The answer is yes. Once you have reached 1 microkelvin, and if you have a ball, a cloud of cold atoms in a trap like that, atoms are undergoing elastic collisions. And if you have in the trap two atoms with energy E1 and E2 colliding, after the collision, they get energy E3 plus E4, E3 and E4, with, of course, conservation of energy. E1 plus E2 equals E3 plus E4. And if E4 is larger than U0, one of these two atoms leaves the trap, and the remaining atom has a much lower energy, and by colliding with the other atoms, the whole temperature of the whole sample decreases. And this effect is very efficient. It reminds what happened when you blow your cup of coffee for evacuating the hot molecule, and the temperature can reach nanokelvin, a few nanokelvin, 10 minus 9 Kelvin. So you see that during the last few decades, there has been a tremendous improvement in our ability to cool atoms. I have represented here, of course, in logarithmic scale, a few temperature, 1 billion Kelvin, the interior of the sun, 1 million Kelvin, surface of the sun. The Earth is at 300 Kelvin. The cosmic microwave background radiation, which gives us information on the intergalactic space, which is the cosmic microwave background, is about 3 Kelvin. If you use a liquid helium cryogenic technique, you get a few millikelvins, and you have Doppler cooling, Sisyphus cooling, and you have evaporative cooling. You read the nanokelvin. So it's incredibly large. I think now we can achieve on Earth, in laboratory, the coolest temperature of the universe. There is no other place in the universe where you can get such low temperature. Of course, if another implication of light shift is the following one, which is very simple. You remember that when you excite an atom with a light beam whose frequency is slightly below the atomic frequency, you have a light shift which is negative, and which is proportional to the light intensity. If you focus a laser beam, tightly here, at the focus of the beam, the intensity is very high, much higher than elsewhere. And if the shift is negative, the energy of the level is shifted down by an amount which is very large. And if this shift varies like that, the atom has a potential energy which is trapped. It is trapped in the bottom of the potential well. That's called a laser trap. So by using a laser beam focused, you can trap atom, and by moving the laser beam, you can put your atom where you want. Another very interesting situation, if you have a standing wave. If you have a standing wave, you have minima and maxima of energy, and the atom can be trapped in the minima. And you have a situation which looks like what happened in solid state, where you have a periodic potential due to the ions of the crystal, and the electrons are trapped in the bottom of the potential well created by this periodic array of potential well. But here you have something which is nice, because by changing the light intensity, you can change the depth of the potential well, and you can change the efficiency with which the atom can move from one well to the other one by tunnel effect. The tunnel effect is large if the light height of the potential barrier is not too high, so it can move freely on the lattice, and if the height of the potential well is very big, it is trapped in the potential well. So you have, by changing the light intensity, you can study what is called the dynamic of the transition between atoms which are strongly located and atoms which are moving freely in this potential well. Now, that's already an application of ultra-cold atom. Let me now give you a few other applications. Another one, which is, there are two big classes of application. The first one is atoms which are extremely cold are moving slowly with velocity of the order of 1 centimeter, 1 millimeter per second. So you can observe them for a long time. And in physics, because of the time-energy uncertainty relation, the longer you observe a system, the more precise are the measurements you can make of them. The width of the resonance, delta nu, is related to the time of observation by an uncertainty relation, which means that delta nu, the width of the measurement, is inversely proportional to the observation time. With very cold atoms, you have long interaction time, and you can make much more precise atomic clocks, and, for example, improve the GPS system and obtain very interesting test of general relativity. Second great class of application, you know that in quantum mechanics, with each particle moving with a velocity v and with a mass m, is associated a wave, which is a de Broglie wave, having de Broglie wavelength, lambda de Broglie equals h over mv. So you see that the de Broglie wavelength is inversely proportional to the velocity. That means that with extremely cold atom, you can get big de Broglie wavelength, and the wave nature of atoms becomes very important, and you can make interference experiment with atoms instead of photons. You can make the Young double-slit experiment with atoms, because the de Broglie wavelength becomes large enough to observe a clear physical effect. And when you have an ensemble of atoms, if the size of the wave packet of each atom, which is determined by the de Broglie wavelength, becomes comparable or larger than the distance between atoms, the waves of the various atoms start to interfere, and you get what is a macroscopic matter wave. and you get what is called now a very important research field. It is called the field of quantum gases. That is gases where the quantum nature of atoms plays a spectacular role. Let me show you, first example, an atomic clock. The principle of an atomic clock is the following one. You have an atomic transition with frequency omega A, with a width delta omega. You draw the resonance curve with an oscillator omega naught, and you scan the resonance. And with a servo mechanism, you correct the frequency of the oscillator in such a way that the resonance, you are in the center of the resonance. So you lock the frequency of the oscillator to the atomic frequency with an accuracy which is determined by the width of the resonance. The narrower delta omega, the better the precision, and you get very precise clock. Example, the first clock which have been obtained by this method are called atomic fountains, which are also quite funny, because you take a ball of, which have been developed by my colleague Christophe Salomon and André Clairon. You start with a ball of atoms here, a cloud of cold atoms here, and with a pulse, laser pulse, you push the atom up. They come up, and they pass through a cavity here, once on the way up and once on the way down. It's a fountain where the water drops are replaced by cold atom. You put them like that, and you can show that the size of the width of the resonance is determined by the time separating the way up and the way down, which can be quite large. And you get stability. The first experiment gave a relative accuracy in the order of 10⁻16, which is quite high, which means that if you have a clock with a relative frequency stability is 10⁻16, that means if you start the clock now, 300 million layers after, it will be off less than 1 second. You see, that's very spectacular. And now, improvements have been taking place instead of using microwave frequency as a frequency for stabilizing the clock, people now are using optical frequency of ions trapped in a lattice, and now the frequency reaches 10⁻18 relative accuracy. So it's very fantastic, and that among the applications, of course, the next step is to put atoms, this atom, cold atom, and putting them out of gravity, because they fall. If you have a cold atom with very slow velocity, if you switch off the laser beam, they fall. So you do the experiment in a parabolic flight, like that, a group of Christophe Salomon in a caravel doing a series of loops like that, parabolic flight, and that works. But now, why it's interesting, because if you have a clock in satellite which are synchronized, you can improve the GPS system, of course. And you can also fundamental experiment is to compare the frequency of a certain atom in the space with the same atom, clock with the same atom on Earth. And the general relativity predicts that you have a difference, relative difference of frequency, which is mgz divided by mc squared. That's the redshift of general relativity. And then one expects to improve the test of this law, general relativity law, by two orders of magnitude. Also, you can also, experiments are being done to test if the fundamental constants of physics are varying in time. Because by measuring the same experiment in 2 years difference, with this accuracy, you can see if something has changed in 2 years. And if the so-called constant, fundamental constants are changing in time. So you see, you can address fundamental questions. And now I finish with the last example, which I will have no time to enter into great detail, which is Bose-Einstein condensation, and which is the following one. Bose and Einstein predicted that Bose started mainly, he studied photons, and Einstein extended photons, which are bosons. And Einstein extended this idea to matter-particle bosonic atoms. And this picture can give you an idea of what happens. Suppose that you have a gas here at different temperature, going lower and lower temperature. At high temperatures, the de Broglie wavelength is negligible, and the atoms behave as particles. And you have a gas of particles colliding on the walls of the cell, contains them, colliding together. And if you decrease the temperature, you start to see the wave packet associated with atom, because an atom is associated with a wave, with the de Broglie wavelength. And when you decrease the temperature, the wave packet becomes bigger and bigger. And at some time, when they overlap, they interfere. And at some time, one can predict that all atoms condense in the same wave function. That's called Bose-Einstein condensation. And the same thing occurs for particles. And you get a macroscopic matter wave. And that, of course, that excited a lot of people. And the cover of Science magazine made an analogy between a condensate and an army of soldiers marching in lockstep. That represents the condensed atom. And you have also some soldiers which are not in the cohort of atoms, and these are the condensed atoms which are not yet condensed. But, you know, it turned out that this gas, quantum gas, has properties which are completely new for atomic physics. They have properties like superfluidity, absence of friction, coherence, which makes them very similar to other systems which up to now were only observed in condensed matter, like superfluid, like superconductivity, also some sort of condensation of electrons in a solid. Coherence, if you have two clouds like that, if you put them together, you get beautiful interference fringes, like in optics. If you have a condensate, and you make it in a trap, you make a small hole in the trap, you have a beam of coherent atoms going from the condensate, which can be called an atom laser. It's a laser where optical waves are replaced by de Broglie waves. You can also observe in such a system, if you try to rotate it, it's not rotate like an ordinary gas. You see quantum vortices, like in superconductors. And you see you have lattices which are very similar to lattices which have been observed by Abrikosov, for example, in solid-state physics. So the emphasis now is put on strongly correlated systems for which mean field theories are no longer applicable. Mean fields theory is a theory where you try to understand what happens to an atom as a result of the mean field which is exerted by all other atoms. Now you have to go a better, deeper way to understand what happens. And let me just try to emphasize why these systems are important. You know, matter waves have very original properties, superfluidity, coherence, which make them similar to other systems which up to now have been observed only in condensed matter, solid state, liquid. The difference with quantum gases is that these properties appear in systems which are much more dilute than a solid state, like an electron gas in a solid, in crystal. And so the atom-atom interaction can be studied more carefully, can take them into account more precisely than in a solid or liquid state. And also something which is fantastic now is you can, in atomic physics, when you have two atoms interacting, you can, by varying the magnetic field, change at very low temperature, you can change their interaction. That's called Feshbach resonance. You can, in a gas, use Feshbach resonance for making this gas a gas of attracting atoms, or repulsive atoms, or perfect atoms with no interaction. So you can change with a knob the strength of the interaction, and you can look how this very quantum behavior change as a function of the interaction. So Bose-Einstein condensate now appear as model system for studying much more elaborate and complex problems in physics. And I mentioned only bosons. Of course, Bose-Einstein condensation occur only on bosons, not on fermions. Electrons are fermions, so they cannot undergo condensation, Bose condensation. But they can form a pair of two electrons with opposite spin appear somewhat like a boson, because two fermions together obey the Fermi statistics and can make a simulation of superconductivity, which is due to BCS, Bardeen-Cooper-Schrieffer pairs. And by changing the interaction, the strength of the interaction, a lot of groups in the world are studying what is called the BEC-BCS crossover. If you have two electrons with opposite spin, if the interaction is strong, they can be engaged in molecules, and molecules very strong, tightly binding. And these molecules also appear as bosons, and they undergo Bose-Einstein condensation. If you decrease the interaction, the two electron pairs are no longer forming a molecule. They are far apart, and they are in BCS state, which is not a molecule, but they still condense. And this is the BCS transition, which explains superconductivity and superconductivity. And you can study, by changing the interaction, the transition between these two regimes, which cannot be observed in condensed matter. So you see that you have now a lot of laboratories in the world studying Bose-Einstein condensation. Let me end with an experiment which has been performed by one of my colleagues, who was actually my first PhD student. It's Serge Laroche, who got a Nobel Prize in 2012, 6 years ago. How can we detect a single photon without destroying it in a cavity? And here also, one uses light shift. The idea is the following. You have a very high Q cavity here with very low loss. So a photon which is in this cavity can live in this cavity for a long time. It can undergo billions of bounds between the two mirrors of the cavity before being absorbed. And suppose that you send in this cavity a beam of two level atoms, E and G, and suppose that you make, at the beginning, before the atom enters the cavity, you make a pi/2 pulse which prepares the atom in a linear superposition of E and G. The atom in this linear superposition enters in the trap. And the level E and G undergo light shift due to the photon which is in the trap. And the two light shifts are not the same. They have different signs. The upper level is shifted up, the lower level is shifted down. So the coherence of diagonal element of the density metric between the two states, once the atom goes to the state, is shifted by the light shift. It's changed. And if at the exit of the trap, you detect the shift, the light shift due to the atom which has crossed the cavity, you can detect if this light shift was due to 1 photon, 0 photon, 2 photon, and so you can measure the number of photons in the cavity without absorbing them, because the cavity, the two-level atom is out of resonance with the cavity, and the photon cannot be absorbed by the atom. You have just the light shift. And you can, in this case, measure, detect the presence, and count the number of photons in the cavity without absorption. So that's another application which was completely unexpected of light shift. Okay, so Let me finish by a picture, a photo of the group in 1966, just a week after the Nobel Prize, Alfred Kastler. And you see in this picture, you see Alfred Kastler is here. Very impressive person, very nice. He was a charisma, which was fantastic. And here in Brussels was his first student. Kastler was very depressed that Brussels didn't get the Nobel Prize with him because he was very important in all the results which have been obtained. And I am here in 1966, so 50 years ago. And here is Brussels, and here you see Serge Laroche. He was starting his PhD here. So in this picture, in the same lab, there have been 3 Nobel Prizes. Alfred Kastler in 1966, myself in 1997, and Serge Laroche in 2012. So that shows you that, I think this picture shows you that research is a long-term project. It's a long-term enterprise. It cannot be done in a week or in a month, or it needs a perseverance and a long time perspective. And it needs to have also a family atmosphere. You know, Kastler was able to put in his group a family atmosphere, and people were happy to work together and very enthusiastic. So I think that's the best thing I can project for ending my talk. Thank you very much.